Good evening. Good evening. AHSA meeting, of course, Wednesday, the 25th of July. But this evening, we're going to have Mr. Andy Jackling. Yes, he is a relation to Noel, of course. And he's going to talk about space weather forecasting. Guest speaker for tonight, Mr. Andy Jackling. And Andy, good to see you there. Thank you. I hope the weather in Adelaide is okay tonight.
Not too bad. It's still pretty cold here compared to Melbourne, but
we have a cold night here as well, so obviously we're going to get a bit more from you tomorrow.
Yep. Generally, the way it works.
Good. I'll hand the floor over to you, and I look forward to your speech.
Perfect. Excellent. Thank you very much for that introduction, and thank you very much for having me tonight. Yes, as you may have guessed, Noel is my uncle. He is the brother of my father. So thank you to Noel for bringing this idea up to me to potentially do this. And I hope you all enjoy. So tonight I'm presenting on space weather forecasting for aviation. So I am a space weather forecaster with the Bureau of Meteorology and have been for about a year and a half now, or just approaching a year and a half. This is what I plan to talk about tonight. A little bit bold. I've tried to cover a lot, but hopefully it's all easy enough to follow. So I'm going to start by just introducing the Australian Space Weather Forecasting Centre, which is where I work, and a little bit of history about how that has come to be, a bit of history about space weather in the Bureau more generally. I'm going to talk about what is space weather. That seems like quite a logical place to start, and then talk through some space weather phenomena, the kinds of things that we are trying to forecast in this particular role. I'll talk, and I've also got a video which I've prepared to show you some of this space weather phenomena in action. I'll talk about the solarized space weather, so that be just who are our customers essentially, and then more so in the second half I'll really focus on the aviation side of things, so the impact of solar activity on aviation, the ICAO side of things, and a service overview there, a little bit on how advisories work and some example advisories. I'll also go over some historical examples of where space weather events, real space weather events, have impacted on the aviation industry. A major geomagnetic storm event we had in April this year. That's sort of to give you an idea of what it's like to go from the start of event through to a geomagnetic storm, and to give you an idea of sort of the day in a life of a forecaster. This was also my first sort of major significant event that I was the forecaster for. So it sort of sits with me kind of in a sort of special way in that sense. And then I'll finish off by talking about extreme events, extreme space weather events more. So Australia has actually had a space weather function in some form or another for more than 70 years. Definitely a lesser well-known fact, I feel like. Since the late 1940s, the Ionospheric Prediction Service was founded, and that's been providing HF radio services, did it for a considerably long time. But to the late 1990s, the IPS evolved to become the IPS Radio and Space Services, IPS-RSS, and through that commenced providing additional space weather services and support. In 2007, that IPS-RSS joined the Australian Bureau of Meteorology. So the Bureau of Meteorology has had a space weather capability since that time. In 2014, it evolved to become the Space Weather Services, the SWS, and that was done under the Bureau's realignment project. Fast forwarding through to 2021, the transformation of the Bureau's space weather capability was announced, and that included a key move of functions from Sydney, where it used to be located, over here to Adelaide. Adelaide, by that stage, had been established as the space and defence hub. Australian space weather capability over to Adelaide to be alongside those partners. So in 2022, the engagement and the forecasting centre functions moved into the BICE building, which is part of Lot 14 in Adelaide. Lot 14, it actually used to be the Adelaide Hospital site, but those buildings have been reformed and now serve different purposes. And the forecasting centre, which you can see here, this is where I spent 11 and a half hours today. That was officially opened on the 6th of October by the Federal Minister for the Environment and Water, Tanya Plibersek. And that's a picture of me there on the opening day with Tanya Plibersek. And also there is the acting Premier of South Australia, Susan Close. That was a real busy day, that one. Definitely feel like I got my 15 seconds of fame on that day. But yeah, a really key moment for us in opening the forecasting centre officially. So this is where I work. This is it. This is the BICE building at Lot 14. And so we are now including the Australian Space Agency, Defence, and the Australian Space Weather Forecasting Centre represents the first dedicated operational space weather forecasting team and centre in Australia. And the Bureau is the only Australian provider of space weather products and provides forecasts, warnings and alerts customised to users in the Australian region. So that's us. And that's a little bit of history about how we've come to end up here in Adelaide. So when I tell people I'm a space weather forecaster, that's not something you hear every day, and it certainly elicits a few different reactions when people hear it. So people have asked me something. They say, "Is there any weather in space?" I even was walking home from work one day, and I had my space weather forecaster jacket on, which says space weather forecast from the back. And a guy came up to me in the street and said, "Oh, I like your jacket. It's a good joke. It's a good one." Like I'm trying to walk around with a joke on my back. It was good. But by far the most common question. So space weather refers to the primary source of space weather is the sun. This is what I spend my day looking at. I spend my day looking at the sun and looking at all the various types of eruptions that it can produce, whether they will impact on the Earth, and forecasting these things. To give you a little 101 on how that works, essentially the sun has extensive magnetic field structures, both within and at the surface. And so that's the first fact I would like you to know. The second fact is that the sun exhibits something called differential rotation. So all that means is that the sun rotates at different rates depending on the latitude of the sun. So around the solar equator, the sun takes approximately 27 days to complete one rotation. And up here at the poles, it's more like 32 days to complete one rotation. So it rotates at different rates. And that's because the sun exists in this fourth state of matter, which we call plasma, which is essentially charged particles. So because the sun has extensive magnetic field structures and it has differential rotation, these magnetic fields can twist and tangle and intertwine amongst each other, both inside and at the surface. And so what can happen then is you get a buildup of potential energy. You've got these magnetic fields twisting and intertwining, and eventually something usually has to give and you get an eruption, and you can get various different types of eruptions, and you get various different disturbances when these structures erupt. And it's those eruptions that are the focus of my work. And I just do want to point out that I'm not looking to scare anyone with images like this. This is quite a scary image in some ways, but I want to assure you, the Earth does have a very effective magnetic field, which isn't going anywhere, which does protect us from a lot of space weather. So just want to make that clear to start out with. Okay, so space weather phenomena. So here we've got this image showing various different eruptions that we can get. So something that people are probably most familiar with is solar flares. And this is a solar flare here. It's a sudden burst of light at the surface. But what I actually want to talk about here is sunspots. So sunspots are the visual representation of what I was talking about in the previous slide. You get these magnetic fields piling up on each other, intertwining, intertangling, and sunspots are a visual representation of that process taking place, because what's happening here is the magnetic fields are so intertwined, they are so clumped together that you're getting like a magnetic plug effect. So the output from the sun is lowered in these regions because the magnetic fields have become too clumped on each other, and the sun can't output what it's normally doing, and you get these cooler, darker regions on the surface. And these are representative of areas of magnetic complexity, and this is where we generally get solar flares from. So this solar flare, if we were looking in this particular imagery, we would likely see some sunspots underneath. And I've got another slide coming up on solar flares, so I will return to talk about that. Coronal mass ejections. This is a coronal mass ejection up here. This is the literal ejection of plasma, a literal ejection of solar material into space. And it's via the same mechanism. You're getting these magnetic fields tangling on each other, and you get eruptions taking place. And sometimes that eruption includes the material that's at the surface of the sun. Part of my job is to figure out, are these clouds of material headed towards Earth? That's a big part of my job, is to model coronal mass ejections and figure out if they are going to reach the Earth. If they do reach the Earth, that's when you get something called a geomagnetic storm. The best way I can describe a geomagnetic storm, just with how you get a normal storm on Earth, which might rattle the shutters of your house or rattle the window frames of your house. A geomagnetic storm is the rattling of Earth's magnetic field by solar material, which has reached Earth. That's sort of the best way I can describe it. And during that process, you can get energy transferred into Earth's magnetosphere. That can cause currents to build out, and those currents can actually work their way down into the ground of the Earth, and potentially into transmission lines and interrupt power grids. So the famous event there is the 1989 Quebec event, where Quebec actually lost its power for about approximately 9 hours due to a coronal mass ejection. Next one, particle radiation. Particle radiation we do get from, it's associated with solar flares. So sometimes you get a solar flare if it's in a certain location on the sun and it's a certain type of flare. You can get a radiation storm associated with that, which reaches the Earth. And again, those three things there, I've got more detail on each of those. Coronal holes, you can think of these as kind of the opposite to a sunspot. Because at coronal holes, you've got open magnetic field lines. You've got the opposite to this twisting and tangling. You've got open magnetic field lines. And this is where we get high-speed solar wind streams from. So you get more output there. And there are various customers impacted by these events. You've got some customers who care about the small stuff and some customers who care about the bigger stuff. So one of our challenges is to try and please everyone. But ultimately, my job as a forecaster is to provide ample warning and forecasts of these phenomena. That really is my job. And that's particularly true in the case of extreme events. So solar flares, I said I'd take a little bit more of a dive into this. So as you can see from this graphic, solar flares impact within 8 minutes. That's the amount of time that light takes to travel from the sun to the Earth. However, this is a little bit misleading. It is true but the detectors that we have measuring the amount of light that's coming from the sun are at the Earth. So by the time we've measured that a solar flare has happened, that means it's already reached us. So when we observe a solar flare, it's happened already. It's actually instant. So yes, it takes eight minutes, but we only detect it when it gets here. So a solar flare is a sudden burst of electromagnetic radiation. It's a sudden burst of light. And the main impact of solar flares is on HF communications. And I'll talk a bit more about HF in a little bit. So we have scales to define the magnitude of solar flares. Not all solar flares are equal. So we have this R scale. R stands for radio blackout. And the higher you go up on this R scale, the stronger the solar flare is. Now, this is all outlined in what we have, which is called the Australian Space Weather Alert System. This defines all our scales, and I'll put a link to that document in the chat if you'd like to have a look at it. But essentially, all I'd like to show you on this slide is that this upper end of the scale, R3, R4, R5, you may have heard of X-class flares. X-class flares is another scale for measuring flares, and X-class being the highest class of flare. And so all I would like you to take from this, I've got these little aeroplane symbols, is that aviation cares essentially only about these higher level flare events. If you've got R0, R1, R2, the aviation sector is not taking any action based on those. It's only the upper level of the R scale. Particle radiation. This is what a particle radiation storm looks like in certain imagery. These particles, they don't travel at the speed of light, but they travel at a high fraction of the speed of light, and therefore they can reach the Earth in 10 minutes to hours, depending on the location on the sun. And for this, we have an S scale. And there you can see what aviation cares about there. So the S scale is defined by the number of particles detected per second by an Earth orbiting satellite. And these storms can last for several days once they've arrived, but they're also the least common type of disturbance that we get. Having said that, we did get an S2 last week, which was the first time that we've had S2 since I've been working at the Bureau. So there you go. But as I mentioned before, these are associated with solar flares. If you get a flare in the right location of the sun, you can get these sorts of particle radiation or solar radiation storms. The main impacts of these are on satellites. Satellites and spacecraft may need to go into safe mode due to those particles penetrating into those electronics. Rocket launches can be postponed in these events. There's a definite increased radiation risk to astronauts and their health in space. Certainly no spacewalks to be taken whilst an event like this is going on. HF communication is also impacted and can be completely unavailable in polar regions whilst these events take place. And there's an increased radiation exposure risk to passengers and aircrew on polar flights. And I'll talk a bit more about that on a later slide. But that's solar radiation storms. Coronal mass ejections. So as I said before, this is the literal ejection of solar material into space. This is what it looks like here on the left. And here on this graphic, it says 0.5 to days. Typically, coronal mass ejections take 2 to 4 days to reach the Earth. If one took 0.5 days, 12 hours, that would be a particularly energetic, high velocity coronal mass ejection. Typically, what we see is 2 to 4 days to reach the Earth. And as I've mentioned before, these can cause geomagnetic storms where that energy gets transferred into the magnetosphere. Now, as you probably guessed, we have a scale for this one as well. It's the G scale. And as per the previous slides, aviation cares only about G3 and above. And as opposed to solar radiation storms, which are fairly rare, fairly uncommon, geomagnetic storms are common. We see them fairly often. We had a minor one today. We had a G1 today. So I've just gone through those 3 scales that we have. but whilst they're extremely familiar to me, I understand that you've just taught them to you now. So I've got this little graphic here, which is going to pop up on various slides in the future to remind you of what each of those scales refers to, just in case. So watch out for that. That'll be at the bottom of some slides to come. All right, so I've just spoken about some space weather phenomena, and now I'm going to show you a video that I've put together of various space weather phenomena. A couple of things before I play this video. First of all, I won't adjust the volume on my side. So just wherever you're watching, if you're on Zoom or if you're in the Melbourne room, please adjust the volume on your side if it's too loud. There's some music there. And the second thing is that the video does contain some elements of flashing due to solar flares. If you feel that you might be sensitive to that, please look away. I know that sounds funny, but if you do feel like you might be slightly sensitive to flashing video, please look away now. It's only a 2-minute video. So with that in mind, I will hit play and hopefully it works. I will make sure I've shared my audio. That would be a good idea. Maybe if Peter Dunn can give me a thumbs up if he can hear it, because he's one of the ones I can see on my little thing here. So let's go. All right. So those are the sorts of things that I get to look at on a daily basis. And yeah, you might be able to tell I do enjoy my job. It's rather good. So I hope that gave you an idea for some of the phenomena that we do observe. So there are a fair few sort of eruptions that that I've mentioned. So some of them create coronal mass ejections. Some of them are just flares, but gives you a little bit of a taste for some of what we look at. And all of that imagery is from the Solar Dynamics Observatory. So solar cycle. One of the very interesting things about the sun is that it does work in a cycle of activity. So the sun works in an 11-year period of activity. So I mentioned those magnetic fields before. So what happens is the sun for a time has rather an organized structure where it's got itself all organized, all the magnetic fields are sitting rather pretty, and then it slowly moves towards this sort of a structure where it becomes more and more intertwined, intertangled, and activity increases. And that's what we call solar maximum. And the way that's measured is through the sunspot number. So the more sunspots you have on the disk, like these, the more activity you have in general. So as you can see here, it follows a nice periodic cycle. And what you'll also notice from this graph is that not all cycles are equal. Some are stronger, some are weaker. And we are currently in solar cycle 25. And if I go to the next image, which is zoomed in on where we are at the moment, first thing to note is that solar cycle 24, the previous cycle, which peaked in approximately 2014, was a very, very weak cycle, very, very weak. As you can see, compared to those previous ones. In 2019, an international panel convenes, and they discuss / argue what they think the next solar cycle will look like. And this red line is the average of what they came up with for solar cycle 25, and the grey shaded area is the full range of predictions that they came up with for solar cycle 25. And if you have a look at the data, this is up-to-date data. Not doing too great so far. We are on track for a stronger than expected solar cycle at the moment. Initial thoughts were that solar cycle would peak in 2025. However, looks like the other interpretation of this graph is that this current solar cycle is peaking earlier than what people expected. So that's possible as well. But essentially, solar activity varies according to this cycle, and right now, activity is ramping up. So who is impacted by space weather? Really, I just want to briefly mention our main customers here. So the first one I'll mention, obviously, is aviation. I'm going to talk about that more in a second. Energy operators, I mentioned before, geomagnetic storms can lead to unwanted currents getting into the earth and into the power lines. So therefore, energy operators are a key customer. Defense, they're always interested in space weather and have various uses for it. Satellites, I've also mentioned that it's important for any satellite operators to have knowledge of incoming space weather. And anyone who uses HF communications is going to want to pay attention to space weather. So HF comms, defense use HF comms, aviation uses HF comms, but also we have a lot of like ham radio operators as customers. So those are our main ones in any case. So onto aviation. I'm now going to talk about more specifically the impact of solar activity on the aviation sector. And there are three main impacts that I will discuss. Those are HF communications, GNSS, which is just a fancy way of saying GPS, and radiation. So those are the three main impacts that I will talk about now with regards to aviation. So HF comms to start with. So before I get started on this, I'm just going to give a very brief 101 on how the ionosphere works, which is tough because the ionosphere is a whole subject in itself, but I shall try. So the ionosphere refers to the ionized atmosphere. So the ionized atmosphere is caused by the sun. The sun, with its ionizing radiation, comes in and ionizes atoms and molecules of the atmosphere. So that means that it strips electrons away from the atoms and molecules in the atmosphere. So that means you've got free electrons in the atmosphere, and they form three layers in the atmosphere, the D, E, and F regions, and that's what we refer to as the ionosphere. So you get free electrons in the ionosphere, and as it turns out, those electrons can be used to reflect radio signals in order to communicate beyond your horizon. So if you've got this person over here and this person over here, and they're beyond each other's horizon, they can't directly communicate, then you can use the ionosphere, and namely the top layer of the ionosphere, to bounce your radio signal down to that person. And that's essentially how HF communications work. So HF communications are used in aviation, and they rely on this ability to reflect radio waves off the ionosphere. The thing about this, obviously, is that the ionosphere is induced by the sun, but then when you have these solar variations, these eruptions taking place, those variations, they readily and easily alter the composition of the ionosphere, and that alters the ability to communicate, and it alters the frequencies you might need to use and things like that. So to give you a few examples, flares and radiation storms that I've mentioned earlier, what happens with those is you get a big enhancement of electrons in the lower region of the ionosphere. So what happens then is your signal doesn't make it through the lower layer. Your signal instead gets absorbed in the lower layer during these events. If you're unable to communicate, it could be for one of these reasons. With coronal mass ejections, you get geomagnetic storms. The effect on the geomagnetic storms have on the ionosphere is particularly complex and beyond my understanding. However, you can get situations where signals will instead penetrate through the ionosphere. So you might have a depression in the, what we call a depression in the ionosphere, and instead your signal, instead of bouncing down, it goes straight through out into space. Now, with aviation, you know, a lot of people in the room will have much better knowledge of this than me, but my current understanding is that HF comms, often on commercial flights, is more of a backup system rather than a primary system that's used. However, for polar flights, that is flights that go across either of the poles, particularly flights greater than 82 degrees latitude, normal forms, the primary forms of communication such as SATCOM, aren't always available. So in those situations, HF comms are more commonly used or a bit more required in polar flights, is my understanding of that in any case. So that's HF comms and why it's important for aviation. And all of these events, by the way, they all impact the ionosphere. GNSS, so Global Navigation Satellite Systems. So as I said earlier, fancy way of saying GPS. SATCOM and SATNAV, they both use this system for navigation and surveillance. And if we have a look at this graphic here, so in this case now, instead of before where we were trying to reflect off the ionosphere, this region here being the ionosphere, now we actually want to go through. We want to go through the ionosphere because we want to communicate with this satellite up here, and we want to find the position of our airplane. So in this case, it relies on the transmission of the radio signals through. And in the case of, you might get an ionospheric storm, which is caused by a geomagnetic storm. So that would be this sort of redder feature here in the ionosphere. That can lead to positioning errors. So you've got your satellite trying to communicate down, but there's a big ionospheric storm in here, and that alters the way this signal comes through the ionosphere, and the position of your plane is incorrect. You've also got this feature over here, which is, I don't want to get too technical, but this is called scintillation. And these are pockets of plasma where, which can occur a little bit randomly. And again, ultimately, all you need to take away is that the signal that you propagate can get lost in those sorts of areas. And in severe cases, you can get loss of GNSS positioning for tens of minutes. So it is important during space weather events, that is. And again, because we're talking about the ionosphere, all of these events are going to impact. So onto radiation and radiation storms. These are only caused by the S scale. The risk here is the exposure of passengers and crew to high energy atomic particles. So as I mentioned earlier, these are associated with flares. As I also mentioned earlier, we had an S2 last week, and the S2 was from this particular event right here. So we had this significant solar flare down here. And as you can see, it's quite broad, and it was also long in duration. And in any case, there was an associated proton event with this particular flare, and those protons made their way to the Earth, and we had an S2 event. So in those cases, solar particles follow the Earth's magnetic field lines, and they do penetrate more easily at the poles. due to the high speeds and energies of these particles, they can penetrate aircraft interior. And following that, they can continue at high velocity into human tissue and cells. So that's not good. That can lead to radiation sickness and things like that. But I will mention that dosage is important. If you're on an isolated one-off flight and you experience, some of this radiation, it might be the equivalent to a few X-rays or something like that. The risk is higher really for crew members who might be doing multiple polar routes over and over again. But in any case, as I'll mention in a minute, if an event like this one here that I'll play here, watch out for the blizzard that appears on this imagery. That's a proton storm right there. If this sort of a storm is happening, flights are not going to go polar routes, so you don't really need to worry. And that's really part of our job, is ensuring these advisories are going out. But this blizzard of particles that you see here, that is a proton storm. It's rather spectacular. So which flights carry the greatest risk? I'll just draw your attention to this diagram down the bottom here, first of all. This is the Northern Hemisphere here, and this is the Southern Hemisphere on the right. And all I really want to show here is that Northern polar flights are far, far more common than Southern polar flights. Also, forgive me, this graphic is almost certainly outdated, but it was the neatest one that I could find. And there are, if anything, even more polar routes than this operating at the moment. In the Southern Hemisphere, just not nearly as many. And the part of the reason for that is simply due to the way that the land is distributed in the Northern Hemisphere. So which flights carry the greatest risk? I'll talk about this with respect to each of the effects that I've talked about so far. So solar flares, where you get a shortwave fade out. Solar flares impact the entire daylight side of the Earth. So if you're in the view of the sun, that's where a solar flare is impacting, no impact to the night side. Geomagnetic storm and a subsequent ionospheric storm, those and HF depressions, those can really impact anywhere on the Earth. It's not really that obvious where it could or couldn't impact. It's really, it can happen anywhere. With radiation storms, the polar flights are the most impacted there. GNSS, it really depends on the type of disturbance that you're getting. Often equatorial and polar regions are the most impacted. Some disturbances can impact globally. With radiation, the risk depends on your flight path and the altitude. So the higher up you are, the more you're going to be exposed to those protons coming down. Polar and subpolar flights, they carry the greatest risk here because those particles make their way down in at the poles. Flights near to North Magnetic Pole, the northern magnetic pole is slightly offset to the geographic pole, and that creates even a slightly more risk because there's just more flights going through that area. So it might be worth just explaining that why do airlines make these polar routes if they carry these sorts of risks? Well, the answer to this is that polar routes are more direct. They have shorter flight times. They have reduced headwinds, smaller fuel burn, big save on costs for airlines to fly polar routes. So yeah, that's really sort of the locations for where these events most commonly occur. And just a side note here, this beautiful aurora picture, this is the visual representation of a geomagnetic storm. So if you're lucky enough to see that on a flight, that's what it might look like. So onto ICAO, the International Civil Aviation Organization. The Bureau works with an ICAO service, and the way that works in general is that there are 4 global space weather centers, and they all contribute to this ICAO service in generating advisories which go out to airlines And there are three categories of advisories. They are HF, GNSS, and radiation, the three that I have talked about. So there are 4 global space weather centres, and the Bureau of Meteorology Space Weather Capability forms part of the Australia, Canada, France, and Japan consortium. That's this one here, ACFJ. And so each consortium operates on a 2-week roster where they become the on-duty centre. So that's where we are. When ACFJ is on duty, then we're the ones who are generating the advisories and making sure that they get out to airlines. And the Bureau's role specifically within this consortium, because obviously the workload is shared amongst the partners, the Bureau's role is to provide high frequency communication advisories. HFCOM advisories is our main job. But we also do perform, for myself as a forecaster, I perform a quality check on GNSS advisories that are produced by France. So France produces an advisory and I look at it, I say, yeah, it looks all right, and then out it goes. And with this, we work with the Bureau's hazardous weather unit. They're the ones who actually push the advisories out. And that's hazardous weather unit is in Melbourne. So here's an example of a few advisories. These are real advisories. You can see the date here. This was only issued on the 20th of June, earlier just last month. And you can see moderate and severe. So there's just 2 very simple scales here for the level of impact of this event. And you get a nice map of the world. And you can see these shaded regions refer to where the impact will be being felt. Now, I should honestly quiz someone at this point to ask what would be the effect, what would have caused this advisory, but I won't do that. But this, you may have guessed that this is caused by a solar flare, because the entire daylight side of the Earth is impacted. And that comes out not only with the graphic, but with this text as well. A lot of technical info in here, but really just the bottom we can look at, which is the RMK, which is the remark. Space weather event, solar flare in progress, impact on lower HFCOM frequency bands expected on the daylight side, higher frequency bands may be less impacted. So there you go. That's an example of a solar flare, which would have been an X-class flare, as I mentioned earlier. Aviation only cares about X-class flares. And so if anyone was using HFCOMs, you should switch to higher frequency bands to maintain your communication. And one more. This is also an HFCOM advisory, this time severe, impacting only those areas. And in this case, again, looking at the remark, this was a maximum usable frequency depression. This was a depression, HF depression event. So this would have been caused by a geomagnetic storm, which caused a subsequent ionospheric storm. So in this case, it's an impact on the higher HFCOM frequency bands. So you can try lower frequencies. The next thing I want to say is, so what do airlines actually do in response to forecast space weather and to space weather that's been observed right at that moment? Well, airlines have pre-flight and in-flight response plans to space weather. And I'll just say before I go into this slide too much further that this is sort of a general thing. Ultimately, each airline will have their own operating procedures for what they want to do with space weather. So this is not across the board what I'm about to show you. But in any case, in general terms, if any of these, and to be clear, we're talking about a forecast at this stage, just forecasts. If any of these are forecasts, there's no planning restrictions on any flight paths that are about to take place. If any of these are forecast, R3, R4, R5, S3 and above, G3 and above, there's no polar planning. There's no flying over the poles. And the reason for that is that with R and G, your HF comms is going to be out. Your HF comms is not going to be available, and that's where you need the HF comms. And with S, well, you've got too much radiation coming in at the poles. So no polar planning if any of these are forecast. What about observed? As many people like to tell me, we don't always get our forecasts right. So sometimes we will observe things that we haven't forecast. So in those cases, if any of these are observed, no problem. Continue on your planned route. If these are observed, R3, R4, R5, G3, G4, G5, that's solar flares and geomagnetic storms. If those are observed, reroute clear of the polar area is the instruction. With radiation events, it's a little more tricky. Not tricky, but there's a little more to it. If S3, S4, and S5 are observed and you're approaching the polar area, you simply reroute clear of the polar area. If you're unlucky enough to be already in the polar area, you're to descend to flight level 280. I believe that's 28,000 feet, and also reroute clear of the polar area. Makes sense. So as I mentioned before, your altitude is going to impact the amount of radiation that gets inside the aircraft. So the higher you are, the worse it is, and you can really significantly reduce the amount of radiation getting in by reducing your altitude. So if you're already in the polar area, descend to a lower flight level and reroute clear of the polar area. That's the general guidelines for any of these events. So I've got a few historical examples now of where space weather has impacted on aviation in real life. First one, in January 2005, there was an R3 level flare and an associated S3 radiation storm. And during this particular event, United Airlines diverted 26 flights to non-polar routes for several days. And this was all precautionary to avoid the risk of HF radio blackouts during those significant events. This increased flight times, increased fuel consumptions, and therefore costs for the airline. And not only that, it causes delays, it disrupts connections to other flights. So a big impact from space weather in that particular case. 23rd of January 2012, there was an R2 level flare and associated S3 radiation storm with an accompanying high-speed coronal mass ejection. And that caused some cross-polar flights to be rerouted due to uncertainties in HF communication. Similar story. On the 4th of November 2015, this one's a little bit peculiar, not entirely sure it's caused by space weather, but I've included it anyway. There was an R1 level flare, and this burst disrupted air traffic control radars at several European airports. In particular, in Sweden, air traffic control systems experienced a blackout, and the country's airspace was shut down completely for over an hour. 6th of September 2017, there were multiple R3 level flares in a row, and that resulted in a significant drop in the availability of European GNSS satellite-based communications. 20th of November 2003, during a G4 geomagnetic storm, the vertical error limit of 50 meters was exceeded for a period of 11 hours. So essentially through this giant red feature here, the positioning of aircraft, I guess in a vertical sense, could not be accurately determined within a threshold that was considered acceptable. So that was a significant positioning event back in 2003. All right, so now I'm going to talk through this April 24, 2023 space weather event, and hope that this gives you an idea for sort of how my job works and follow an event from start to finish. So a few days before April 24, because the event didn't start, the event started on 24th, but the conditions which led to the event started earlier. Essentially, I came in on a Saturday morning, working my weekend shift, and the sun looked like this in terms of sunspots. This is the wavelength we look at to look at sunspots. And, you know, I'm looking at this region here, thinking that's looking pretty complex. This region's just coming around, it's rotating into view. That might be worth watching. I wasn't thinking too much about this one here because it's almost the dimmest one on the disk at that time. But as you're about to see, what I observed next from that particular region was fairly significant. So I've got this video here. Hopefully this plays smoothly, but essentially first thing, Saturday morning, 6 a.m. start, and this is what I see on the sun. So what you're seeing there is a moderate sized solar flare. In fact, it's only an R1 flare. It's not that big, but I'll play that through again. And what you notice about this particular flare is, first of all, as you might have seen with some of the previous flares that I've shown, they can be very pinpoint. Flares can be very pinpoint from a very specific location, but this one is not. This one is very elongated. It's covering a large area. It's extending a long way across the disk. And that was the first thing of note. The second thing of note is just how incredibly central this flare is. It's actually, if you imagine this observation is taking place from we've got the Earth view here. This is the Earth facing the sun. So this flare is facing directly towards us. So the next thing that I would look at is what we call H alpha imagery. And in H alpha, this is from a ground-based telescope. We have one of these in Western Australia, which the Bureau uses. This image here is actually from one in Spain, as you can see. And what you're looking at here is these dark sections on the sun. So these dark sections are called filaments, and this is cooler, denser material that's suspended above the surface. And what can happen with filaments is that they can erupt, they can fly off the surface, and those become coronal mass ejections, and those can become geomagnetic storms. So as you can see, there's a sizable filament right in the center of the disk. And if I go to the next slide, if you watch very carefully, the flare happens just in here, and this filament gets knocked off. So the flare sort of that activity can knock filaments off, can cause filaments to erupt. And that's exactly what happened in this case. So that filament erupted as a result of that flare that I showed in the previous slide. So the next step is, do I have an associated coronal mass ejection with all of this activity? And the answer was yes, because if you watch clearly here, sorry, that does go rather quickly. This was the best I could do, but this will repeat there. What you're getting there is what we call a full halo coronal mass ejection. So that's what it looks like when a coronal mass ejection is coming towards you. It's a full halo ring. And so the sun, by the way, is being purposely blocked out by the detector so that we can see the more diffuse material around the outside. And so what you see here, there, is the coronal mass ejection associated with this event. So then my job as the forecaster is to model that coronal mass ejection. This is a big part of my job, and it's one of the things which comes with a lot of uncertainty. It's difficult, it's not always easy, but essentially I fit a cone around this coronal mass ejection, and I make a model. And here's what my model looked like when I outputted it. Now, you only need to really refer to the top panel here. The top panel here, we're looking on top of the solar system, like we're looking down into the solar system. And this is the sun, and the green dot is the Earth. Don't need to worry about the other dots. And this big red feature here is the coronal mass ejection that I have modeled as a result of the eruptions that I've observed. This cutout here is like you're looking side on, at the Earth. So you can see the up and down. You can see whether it's going under the Earth or you can see whether it's going over the Earth. And what you can see is that in both of these panels, we're getting pretty much a direct hit from this coronal mass ejection. And you can see this green line, the plasma density at the Earth goes up considerably. And the forecast impact was for late on the 23rd of April. And around came late on the 23rd of April. And I realize this plot is rather busy, but all I need you to look at is really this purple graph in here. And as this is what we call the solar wind speed. So the solar wind speed's trucking along, doing not much, cruising along, and then bang, you get this, what we call a step increase in the solar wind speed. And that is the arrival of this coronal mass ejection. That's what it does to the solar wind speed. It get a sudden increase there. So forecast observations and outcomes. So what did I do? Well, I forecast G2 to G3. So once you get that model output, it's your job as a forecaster to make a G forecast. What do you think this will be? G1, G4, G5, whatever it is. I forecast G2 to G3, and then we have a significant event procedure which gets enacted when from G3 and above. So naturally, my manager said to me, you need to choose between G2 and G3. Tell me which one you think it is. And I said G3. So I erred on the side of the larger event. And the interesting thing about space weather is that we have other global centers who are also forecasting the exact same event. So that does make it interesting. And for the record, we put our forecasts out before the rest of the world, so there's no copying them. You have to commit, you have to make your decision. So other global centers, their forecasts varied from G1 to G3. So you can imagine I'm a little bit worried when I've said G3 and someone else is forecasting G1. Nonetheless, what happened was G4 was observed. So G4 geomagnetic storm, as you can see from that graph down there on the bottom right, all of those red bars, so each bar is a 3-hour period, and each of the red bars represents a G4 geomagnetic storm. So you had G4, G4, G3, G4, G3, G2. So a significant geomagnetic storm which took place. There were also S1, solar radiation storm conditions observed. R1 is just from the initial flare. That was the R1 flare that I showed you earlier. So during this geomagnetic storm event, airlines indicated significant issues with HF communications during the storm. That's from everything that I've presented so far, that's to be expected, but it did actually happen in practice. What also happened was that Qantas rerouted all their polar flights as a result of the Bureau's forecast, and they rerouted them to non-polar routes north of 60 degrees south. So that impacted flights from Sydney to Johannesburg and Sydney to Santiago. I believe it added some hours of travel time to one or both of those flights. So hopefully that gives you an idea of how we progress through an event. That's a little bit of a crash course, a little bit of a day in the life. That was my first significant event that I was a part of. So on to extreme events. This is my final slide for tonight. So G4, as I just mentioned, that particular storm, G4, it's not that rare. It's not extreme. So we actually get 100 G4 storms per solar cycle. So it's not uncommon, and it's not an extreme event. It's significant, but not extreme. So what do I mean when I say an extreme event? Well, we have a benchmark for what is considered the extreme event, and that benchmark is called the Carrington event, and that occurred in 1859. With that event, you had an Earth-directed coronal mass ejection which travelled at more than 3,000 kilometres per second. It had only a 17-hour travel time to reach the Earth, and it induced G5 geomagnetic storming comfortably. At the time, in 1859, the only form of technology that we really had was telegraph machines, and those all failed, and even telegraph operators were getting zapped through the machine as a result of this incredibly strong geomagnetic storming. So what I want to note is that if I just play this video through, looking at the solar cycle again, we have become a space, spacefaring civilization around this time here. And this extreme event occurred in 1859. And the point of this here is to show that we have not had a Carrington event in today's modern, interconnected, technology-reliant society. So it has not been observed since the dawn of the space age. Now, that's not to make anyone worried. These events are extremely, extremely rare. And it's very, very possible that I can go through my entire career and not observe an event of this magnitude. And honestly, I hope I don't. But what we are doing at the Australian Space Weather Forecasting Centre is we are aiming to best prepare Australia for that 1 in 100-year event. And we want to make sure that our main customers in defence, in energy operators, whatever it is, are adequately informed and put Australia in the best position to respond to an event like that. And that very much includes the aviation sector as well. So on that note, that is my final slide. I will finish up there. Thank you again for having me, and happy to take any questions.
And a comment from Dave Prosser here. GNS is the general, I call it the American expression. In the same way you've got an expression for Europe and also for Russia. And those are the ones that we commonly call GPS, motor cars, airplanes, just GPS rather than GNSS. And the other one that I've come across in flying is that there are certain sectors of Australia that are not covered by VHF radio. And you can fly from here to Queensland, for example, to back to New South Wales, and you might not be able to be in VHF comms with Melbourne Centre or Brisbane Centre. And it's rather strange to be flying along and suddenly the VHF radio just simply dies. And this is okay for a private pilot, but for a commercial flight, of course, they require to have comms from startup to shutdown, and they need to have HF radio to go through those areas that are not covered by VHF radio. So an interesting aspect there that you raised tonight with us, and I do thank you very much for that. Dakota Dave.
Thanks, Andrew. That was most entertaining, most enlightening. I was one of those skeptics when I heard it was going to be about space weather, like the person observed the back of your jacket. I thought, space weather, there's nothing out there. How could it possibly be? But I now feel very enlightened, and so thank you for that. My question is, did I understand there are 4 centres worldwide like yours? Your centre is one of them in Adelaide, and throughout the world there are 4 only?
No, so those are only the ones that contribute to ICAO.
No, I've got no sound now. Hang on.
Yeah, you got me?
Yeah, thanks.
Yeah, so no, there are more. Those 4 that I mentioned, they're just the ones that contribute to the ICAO service. So there are multiple other space weather centres out there.
And you all speak to each other? It's a worldwide network, or?
I would say it's becoming increasingly collaborative. I can't say that we talk to all of them, but certainly the UK and the US we talk to more frequently. Other centres, it's increasing.
It's not directly related, but can you tell us what that apparent geostationary satellite is in our western skies that you see in the evening?
A geostationary satellite that's in your skies.
It looks, well, it doesn't go anywhere, so it must be geostationary, and it's very bright when in the evening sun.
Yep.
Does anybody know what it is?
It's you're not referring to Venus, which is currently in the evening sky.
Yeah, I thought of that too, but it seems to be a satellite.
Okay, so I know that Venus is there because I've been looking at it on my walk home every night. But aside from that, there's a website that I used to use called heavens-above.com, and you can look up any satellite passovers there. So if you go to that website, you might find that there's a geostationary satellite there.
And it might be Venus. Thank you.
Yeah.
Another question, Andrew, from David.
Yep.
Are your observations all from Earth, or do you use satellites to capture the storms coming?
Yeah, so it's a combination. So we have some ground-based telescopes which look at the sun all the time, namely one in Western Australia at Learmonth. However, all the imagery of sunspots and flares and things like that come from space-based satellites, which are operated by the US. In terms of monitoring a storm that is impacting Australia, we have magnetometers all around Australia, and they measure the level of geomagnetic disturbance in Australia. And similarly, we have a network of ionosons, which measure the ionosphere and things like that. So it's a combination of ground-based instruments and space-based instruments.
Thank you.
Roderick, do you want to unmute yourself?
I think I am unmuted. Good evening, everyone. I've got to restrict my questions to Andrew to those things which are his sphere and not those which affect how the flights run. I did an umbrifile flight over Antarctica for one of the eclipses of the sun, and the highlight of the flight was we have Bailey's beads. Now, are they just normal flares? The ones you've described are extreme or larger than normal?
No, so I must say I have to applaud this question. I'm so happy to hear this question. So Bailey's beads are a fantastic effect of a solar eclipse. They are not solar flares at all. Bailey's beads happen because during a solar eclipse, the moon is covering over the sun, and the disks are approximately the same size. However, the moon is not a perfect sphere. It's not a perfect sphere. It's got things like mountains and valleys on it. So what happens is, as it just covers over the sun, you're getting the effect of the sun shining through those valleys and mountains, and that creates this beads effect where it looks like the sun has become beads. So that's all that is. It's actually not related to flares at all, but a magnificent effect that I really want to see myself, and I haven't. So
and I have.
yeah.
Thank the and the other question, one of the 4 ICAO partners is a China and Russia consortium. Are you people technicians? You are independent of world politics. You coexist regardless.
We coexist peacefully. It's it's an interesting one. Yeah, I don't have anything more to say other than it all just works. We all just work together, and I guess we are maybe immune from the world politics in that sense. But it all works like clockwork. Yeah.
Got another question.
Another question here. Another question to you, Andrew, from David. I'm not trying to hog it, but it fascinates me, this. You say that the dangerous flying is over the poles, and that if you have these flares, then they get the aeroplanes to divert away. I want to know, what about the people that are working, say, in the Antarctic? They're there for 6 months. Now, are they subjected to these radiation waves that the aeroplanes are avoiding? What risk are they under?
Much less risk, because they're at the surface. So the reason for that is that when the radiation comes in at the poles and enters the atmosphere, straight away collisions will start happening with the radiation and the atmosphere. So it's colliding all the way through. So as it goes down and down and down, it's losing energy all the way down to the surface, losing energy to the point where for most events, it's just not going to be that dangerous at the surface. So there's much less risk at the surface compared to flight altitudes.
Thank you.
Okay, Peter.
G'day, Andrew. Jeff Hearn. Like very early on in your talk, you were talking about magnetic influences, and I can't help but think, is there any correlation between that and the Bermuda Triangle with aircraft and compass readings, etc., etc.? Thank you.
Not to my knowledge. I'm not aware of any such correlation. From my understanding, the Bermuda Triangle, part of the effect anyway is that there's a lot of common routes, a lot of common, I think, shipping routes through that sort of area, which statistically speaking is going to lead to things happening through that region. But I certainly can't make any correlation between geomagnetic activity and that effect.
Peter Dunn. Yep, Peter Dunn in Brisbane. I'm an electrical engineer, retired from Powerlink Queensland 13 years ago. I know that we had a collaborative project with the other transmission network companies across Australia to measure neutral currents in some transformers. I know at Middle Ridge, though, we measured the leakage there in case of any of these events. I was just wondering whether you have a direct hotline to the AEMO operations centre if there's something urgent that comes up.
Short answer is yes.
Yeah.
They are someone that we are in direct contact with, and that during the G4 event that I showed, that I was in direct contact with. And yeah, there are various things being worked on to ensure that the power grid remains unaffected in Australia during one of these events. It is very important. Yeah.
Do you have access to those devices that we installed at Middle Ridge and other places, or do you rely on us to pass that on?
I don't. I'm not
Okay.
sure. I don't believe
Right,
so,
that's
but
right.
I don't think so. Yeah.
Thank you.
Andrew, I've got a question. David Knight in Melbourne in the,
Mhm.
in the meeting. Airline pilots flying high, 39,000 feet. As you say, they're more exposed than probably most people. In view of the fact they fly at night very often, don't they? I mean, whenever I fly to England, it always seems to be at night or coming home. Is that one reason why they might fly at night, or probably not?
I
But
don't think so. Certainly, when you get these radiation storms, they're coming in they can actually come in on both sides. So I wouldn't have thought there's too much difference between day and night. The main difference is with flares.
Okay, and the other thing that I've heard is that airline pilots are subjected to radiation, which is probably equivalent to an X-ray, but I don't know how often that is, but it's reasonably frequent, like an X-ray every week or something like that.
Yeah. I do have some stats on the slide that I didn't mention actually, so I'll try and find those. But you're right. You're essentially getting the equivalent of a few X-rays. So what I've got here is the recommended annual maximum dosage for any person in a year is 10 medical X-rays. And a round trip flight over a polar route is approximately 2 medical X-rays. So 5 of those polar routes, and you've got the maximum yearly recommended dosage. So I think for that reason, as you know, I'm not a expert in flight routes or roster planning for airlines or anything, but my understanding is there's a very limited number of repeated flights that a pilot or crew members can do for polar routes in order to reduce that exposure.
Thanks, Andrew. I'll hand over to David.
Sorry, David, back again. Sorry, Andrew. David Anderson back again. So taking it a step further, what about the people manning the space station? Now, they're out there all of the time.
Yep.
What's the risk for them?
Yeah, there's certainly a risk, particularly during the most risk would be radiation storms. They do have on the International Space Station an area which has better shielding from these radiation events, but it's not foolproof or anything like that. And you're absolutely right. This is as I understand it, this is the risk they know they're taking when they go up into space. They are absolutely at a higher risk of cancer, and they are absolutely at a higher risk of developing cataracts. It's very common in astronauts. So it's really part of the risk that they take.
Oh, Noel wants to.
Okay, another
And
question
Phil
from the
Vedray
room.
as well.
Yep, Phil will have to unmute himself. There's the
Right. Andrew, the question comes from one of our past conversations, but it's a Dorothy Dix. But do you have access to the Prime Minister?
I don't have direct access to the Prime Minister. However, one of our main, it feels wrong to call it a customer, but one of our main areas that we talk to during significant events is the National Situation Room. So we do talk to the National Situation Room. We're in contact with them during significant space weather events to make sure that they are informed. And through that measure, I assume the Prime Minister is informed through that measure. So I'm a link away in the chain of being in direct contact with the Prime Minister.
Andrew, Phil Barbara here. That was absolutely fascinating presentation. Thank you. And as somebody who works in the business on the operational side of this every day, so it's a part of the whole behind the scenes thing that I knew nothing about. So it's great. Anyway, my question for you though is, how do you become a space weather forecaster?
It's a great question. Took me a long time. So I did, when I was 12 years old, my dad, who's on the call, he showed me Venus. We've also spoken about Venus on the call as well. He showed me Venus in the night sky, and I was absolutely captivated, and I was just obsessed and fascinated by the universe at that young age. My parents very kindly forked out the money for an expensive telescope. Noel also gave me his father's telescope and accelerated my interest. And then I went on to study, majored in astrophysics at Monash University, and then I did a master's in astronomy. And even once I'd done that, it was still, what am I going to do with this? It's space-related jobs are, it's needle in a haystack type stuff. Generally, it's, you go into research or you teach. Those were generally the two pathways that I got told when I was at uni. These are the two things you do. You either go do your PhD and go into research, or you go and teach or do something like that. But what I realized, I guess, with the Adelaide space sector up and coming, was that we had this third option of space jobs, space sector jobs. And I learned that the Bureau of Meteorology had a space weather section several years ago. And when I learned that, I became a regular refresher of the Bureau's job vacancies page. No joke, I had it bookmarked, and I would pretty much load it every day and have a look. And I also got in touch with them during the start of the COVID-19 pandemic. And I got in touch and I just said, how can I improve my employability with you so that I can work with you? They gave me some pointers very helpfully. And then really, when this transformation happened, this switch from Sydney to Adelaide happened in 2021 to 2022, that opened up vacancies because not everyone wanted to move to Adelaide from Sydney. So there were 3 space weather forecaster positions available. I applied, I got in there, and was lucky enough to be chosen. So that's how I got to be where I am.
Did you have to do much in-house training, or how do you learn the technicalities of it all?
Yeah, it was a long training process. I believe at least 6 months, something like that, to learn to be a space weather forecaster. I had excellent guidance from those before me, and it was a very intensive process to become competent as a space weather forecaster. And honestly, I still feel like I am learning new things each day. And the key variable in all of this is the sun. The sun continues to surprise me in what it can do and the different events that we can get. So the sun will always ensure I keep learning.
Okay. Any other questions? Peter, your hand is still up. Is that another question?
Yeah, the second question, sorry. Andrew,
ahead.
does Geoscience Australia play a role in monitoring?
Yes, they do. Geoscience Australia, some of the magnetometers that we use to measure geomagnetic activity in Australia, they are owned by Geoscience Australia. So absolutely the answer is yes to that question.
Thank you.
We've got
Is this program being recorded so we can see it in the future? Because it's a fascinating thing, and it's a lot to take in one evening.
Yes, the short answer is yes. And Andrew will review it and make sure it's okay. And then in time, we'll get it edited and then added to the AHSA website, where you can see a lot of other videos of our meetings.
Great. Thank you very much. And thanks, Andrew. Terrific.
No worries. And I've just put a few different links in the chat there. And yeah, I'd just like to say thank you, first of all, to Noel for setting this up, to David, and thank you to the Aviation Historical Society more broadly for having me tonight. Hope you enjoyed it.
We have, and Andrew, from myself as president of the HSA here, and also our audience in the Rafa building here. Thank you very much. We have enjoyed being enlightened about space weather forecasting, and you have put a lot of work into the presentation, and I do thank you personally for a very well structured and organised event there. So once again, thank you very much. I do appreciate your time tonight, and we'll go from there. Thank you.
No worries. Thank you. Thank you very much. Thanks.